The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So this is a review session number 5, I guess it is. And it comes before an exam next Tuesday, and actually there'll be a further review session number 6 on Monday, right before the exam. So, so maybe today there's a homework problem set on sections on chapter 2, mostly the oscillating masses and springs, and today's lecture that you see traces of networks, and masses and springs also the static case. So I'm open, as always, to questions. Yes, please. Thank you. Right.
2.2 number 6.
2.2 number 6. Okay, yeah. So this is, and of course, you understand, so I'm happy, that's a good question to discuss, and maybe number 7 people will have something to say about. Good. Yeah, so that's just fine. So let me start right in on those. So number 6 is the fact, I mean, everybody understands that when energy is conserved, that's an important thing. And so the question is, first, when is energy conserved in the differential equation, in the equation we're trying to solve? And if it is, then we want to know, we would like to choose difference methods that also conserve energy. They may not be exactly right, they may not be exactly at the right point on this circle if we're in that model problem, but still on the circle. So, and the point is that the trapezoidal method does stay on the circle, and of course the differential equation stays on the circle. Can I, and I put quite a bit into this problem 6. So this is 2.2.6, and let me try to say something about that. Okay. So first of all, there's the continuous problem, du dt equal au. When does that conserve energy? And then there's the discrete problem, which we know that Euler doesn't conserve energy, because we've seen it. The computer shows you right away. It spirals out from the circle, it spirals in for forward and backward Euler, but trapezoidal method, is that the one that turns out to be well? Okay, so it says, it refers to equation 24 as the trapezoidal method, and let me try to follow that notation. Yeah, so this is, the trapezoidal method is this one. Did we get music there for the trapezoidal method? Okay. un plus 1 equal I plus a delta t over 2 un. Okay. Right. Okay. So that, and actually problem 7 that you maybe want to discuss too is the question of how accurate this is compared to the differential equation. Everybody should see that this really came from, the original way to look at this was un plus 1 minus un over delta t, that approximated the derivative, equals a, and then I'm taking half at u and at the new time and half at the old time. So it's got that centering that we suspect will give us a little extra accuracy. Okay. So 2 questions then. One was the stability. So problem 6 was the energy conserved. And problem 2.2.7, if I anticipate it, is the order of accuracy. So these are both topics that are extremely important in choosing a difference method. We're very happy to know that this well, we would like to know first, when is energy conserved there? What differential equations have conserved energy? Physically, we kind of can see them coming. You know, if the physical universe is not being, is somehow lots of physical problems. We see those masses and springs oscillating, and we say, okay, nothing's coming in from outside. How could energy there would be the sum of the kinetic energy of the masses and the potential energy in the springs. So energy passes between kinetic, when the mass is zooming past equilibrium, and potential energy when the mass is stretching the spring. So we've got two cases. So, and we would hope, and this trapezoidal method comes through, that energy is conserved. So can I just begin with this one? Maybe I always ought to say, because you guys are also thinking about the quiz. And so this, for example, this question about how to find the order of accuracy, that's, I'll speak about that. But let me just say, that's not something that we've done in enough detail that I would expect you to be quick on the quiz and just be able to do it out. I'll try to choose questions on the exam that you really have had more practice with. But this is certainly important, so it was definitely right to put on the homework. And this is important. Okay, so let me tackle this one. First, the differential equation. So by energy here, I'm meaning just the length of u squared. So let me, so now I'm looking at energy conserved. Okay, so I'm hoping energy conserved would mean that the derivative of u squared was 0. That's what conserving energy would mean. And my question is, which differential equations, what's the condition on A, in other words, that I should, how would I recognize from this matrix A that I have this interesting property? Okay, so let me just show you what I would do. Okay, another way to write u squared is u transpose u. These are vectors, of course. Okay. Okay. So what's the derivative of u transpose u? See, I've got my equation is telling me what the derivative of u is. Here I've got the thing squared. Okay. I have a product here, right? I have u's times u's. So I'm going to use the standard. They happen to be vectors, so if I want to use like freshman calculus, I'd have to get down to the scalar to get down to the numbers, but I absolutely could do that and just follow them along, component by component, or I could try to do it the whole column at a time. And let me try that. That it's going to be the product rule, right? It's in some form that I'll have this guy times the derivative of this plus the derivative, I'll keep them in order, the derivative of this thing times this guy, right? That should be, that's the product rule. Okay, now what do I know here? I know that the du dt is au, right? So this is u transpose au. And I know du, is that dt, meant to be dt? So so du dt is au again. Look, this isn't difficult. It's au transpose u. And the question is, when is this 0? Okay? So those were the two terms from the product rule. And notice they're not exactly the same. This is U transpose AU. And what's this guy? U transpose A transpose U. So if I put them together, I have U transpose times the A and the A transpose times U. And I'm hoping that this will be 0 for all the solutions that I've come up with. So the condition is simply that A plus A, we want that to be the 0 matrix, A plus A transpose. If in other words, if A transpose is minus A, that's the good one. If A transpose is minus A, this is 0, that's 0, that's 0, that's 0, energy is conserved. So the energy is conserved when A transpose is minus A. It's for the antisymmetric A's that energy is conserved. And of course, this all makes sense. What are the special solutions to that differential equation? The special solutions to this equation are e to the, this is connecting now with things that really are basic. The special solutions, the pure eigen solutions, the ones that follow their own paths, are the e to the lambda t x's, right? Where x is an eigenvector of A and lambda is an eigenvalue. Those are the guys, and we expect to have n of them, and we expect a combination of those to give us the general solution and to match the boundary condition. So these are these n of these guys with n different eigenvectors and their eigenvalues are the heart of problems like this. And of course, that's the additional homework problem that wasn't in the book, but I added as an additional problem was exactly that, to get you to practice with these eigenvectors and eigenvalues. Okay, now what's the deal? I want to connect this energy conserving with this picture of solutions. When would this keep the same energy? When would the energy of these, of that, when would this have constant energy? Constant length. The length would be constant, since x is certainly, that's a eigenvector, whatever it is. This is what's changing. And now I want to know, when does the length not change? Well, the test would be that this number should have absolute value 1, right? If this keeps absolute value 1, then in the eigenvalue picture, I have energy staying the same. Okay? Now, when will this have magnitude 1? Time is running along. This is e to the lambda t. So which lambdas? 0, certainly. But now there's more. You got to know the others. What other lambdas give me this thing stays on the unit circle? Absolute value 1. Key question you must know. Lambda could be imaginary. Lambda could be imaginary. Right, lambda could be imaginary. E to the I omega t. Those, we don't, that's just like basic fact about complex numbers, that if lambda is imaginary, we would have the cosine of something t plus I times the sine of something t, cos squared plus sine squared being 1. We'd be on the unit circle. So we want, from this picture, we would want the lambdas to be pure imaginary. And now a little next step, what we'd like for the eigenvectors. Because the real solution will not be just one of these guys, but a combination. So when we have a combination, each one is doing its thing. Each one better have lambda imaginary. But more than that, we would want the x's to be perpendicular, because if the x's interact, then this guy, one of these, you will say there's only one there, but I'm thinking of n of them there. A combination of, say, two of them. Suppose I have an e to the lambda 1 t x1 and an e to the lambda 2 t x2. When does that conserve energy? Well, each one will, but the combination will be fine if the x's are perpendicular. Because if I have perpendicular vectors, then the length of the whole combination is, by Pythagoras, is just 1 squared and the other squared, and each of those pieces is constant. Let me say what I'm trying to say. That the eigenvalue, eigenfunction picture also tells us that we would like imaginary eigenvalues and perpendicular eigenvectors. And that is exactly what you get from A transpose equal minus A. So A transpose equal minus A is exactly those matrices, anti-symmetric matrices, have perpendicular eigenvectors, just like symmetric, but the eigenvalues are pure imaginary. Instead of all being real, they're all pure imaginary. In other words, that answer and the discussion here came to the same conclusion. Okay, that A should be anti-symmetric. Okay. Now let me look at, ready, is that okay? So that's a discussion which is worth knowing about differential equations. When is energy conserved? Now I want to do, or the problem asked me to do, what about this difference equation? When is energy conserved there? And I guess, I believe it will be. If this is the requirement for the differential equation to be okay, to conserve energy. And so I'm going to need that in this one. And is that enough? If I have this A transpose equal minus A, anti-symmetric, it was good for this, does it also do the job here? Is this trapezoidal method just cool so that it will conserve energy too? And the answer, I think, is yes. And the problem was to prove it, or to see why. Why is, so what do I now want? If you don't mind my erasing, I'm now going to look at the discrete guy. So now I'm looking at when is un plus 1 squared equal un squared. That's what I mean by conserving energy in the discrete case. At every step, same energy. So now I want to look at the energy in un plus 1 compared to the energy in un, and I want to see that this holds. Probably there's some smart way to do that. Now we're down to just like the math question. You know, math is always looking for some. You just sort of do the right thing and stand back, and poof, it works. Okay, so what's the right thing? Hopefully, I have helped you and me by saying what would be a good idea to do here. Can I just look? Okay, it says, oh, does it say what to do? Yeah, it says multiply by un plus 1 minus plus un. Take the dot product. That's interesting. Take the dot product. So why did that work? Take the dot product of both sides with un plus 1 minus un. Did anybody succeed with this idea? But that's the idea, and hopefully we'll get it to work. That if I multiply both sides by un plus 1, plus un, maybe better if I look at it this way. I'm sort of okay to do it that way. Suppose I multiply both sides. So now I'm following on this idea. That equation I've rewritten here, and without practice, I don't know which one is the good one to start with, but I'm pretty okay with starting with this one. So what's my idea? That's my equation. Now I'm going to multiply both sides by un plus 1 plus un transpose. Now I don't have room to do it, unfortunately. I want to stick in here un plus with a plus sign in there. And of course, I have to do the same thing here. Okay. You okay? Do you see what I'm doing? I want to show that this equation, which is the same as this equation, has this property, which is a copy of this property. I mean, here would be another way to do it. I mean, we could do it the way we're going to do it now is sort of compares with the way we started with the derivative of the norm squared. I could also ask the same question by following eigenvectors. I'm guessing that here the eigenvalues un plus 1 is, you see, I could do it both ways. Maybe having just done eigenvectors, let me do this one by eigenvectors. So what are an eigenvector of A, one of x itself, is what happens to an eigenvector? Suppose u0 is an eigenvector x of A. What's u1? Yeah, you really should see this question. So if u0 is the eigenvector x, then what is u1? Let me just write here, ax equaling lambda x. So these are the eigenvalues of A. And now I want to, and we've learned that they're pure imaginary in this case when we're ready to go. And now I'd like to know that that we get the good thing here. Okay, so what if un is an eigenvector? What is un plus 1? Okay, so can I just do that? Un plus 1 is, what do I have on that right-hand side? X. And what is ax? It's lambda, right? It's lambda x. So all this is 1 plus lambda delta t onto x. But now I've also got to hit it, bring this guy over here, its inverse, and see what that does. Now it's the inverse, so it's going to have the same eigenvector, and the eigenvalue is going to go in the denominator, and it'll be 1 minus delta t over lambda delta t over 2. Okay, so that's un plus 1. Do you see what's happening here? The eigenvector x, if we start with that eigenvector x, we come out with a multiple of x, and this is the multiple. So each finite difference step multiplies by a number, just the way in the continuous case, we were multiplying by e to the lambda t, and in the discrete step-by-step case, we're multiplying by that number. Actually, this is why problem 7 is important, because if we want to know how accurate the comparison is, I want to compare e to the lambda t with that number. But so problem 6 is asking about a question about that ratio, and problem 7 is asking another question about that very same ratio. Now, what's the question for problem 6? When will this vector have the same length as this x was un? What am I? So I started with a un. I multiplied by this number to get un plus 1. When do they have the same length? When that number has absolute value 1. So that's my, if I'm watching eigenvectors, this guy had absolute value 1 because lambda was imaginary. Now, what about this guy? Lambda's still that same lambda, imaginary. What can you tell me about 1 plus, so lambda is some I omega delta t over 2. And down here I have 1 minus I omega. That's the lambda delta t over 2. I believe that does have absolute value 1. Anybody tell me why? So this is checking that energy is conserved for each eigenvector. The energy, because the eigenvector is multiplied by that number, and that's some number, it's some complex number, but I believe it has absolute value 1, and I believe you can tell me why. Yeah? Because they're complex conjugates. This numerator and the denominator are complex conjugates. In the complex plane, here's the 1, and I go up an e to the I go up by I omega delta t over 2, or in this one I go down by e to the I, but those lengths are the same. That numerator, the length of the numerator is that guy, the length of the denominator is this guy, and their ratio is 1. So I think that this gives us the point about complex numbers, that a complex number and its conjugate automatically have ratio of magnitude 1. You see the difference between Euler's method. So Euler's method, forward Euler would not have had this implicit, this stuff on the left side. It would all have been on the right-hand side. Forward Euler would have been about I plus A delta t A. And what are its eigenvalues? 1 plus I omega delta t, right? With no, we're not dividing by anybody. It's this part is up top too. So it's 1 plus I omega delta t. Now, does that have absolute value 1? Well, you know from the way I'm asking the question. What can you tell me about the absolute value of that, of the forward Euler growth factor? Greater than 1. Because this is the 1, and this is the I omega delta t. Maybe it went up twice as far, and there was nobody to divide by. It's bigger than 1, so it blows up. And the backward Euler had only the 1 over 1 minus I omega delta t. So the backward was like this, like 1 over it, and less than 1. But this balance has absolute value equal 1. So, okay, that's the sort of heart of what's going on. Can I, before I tackle the question using the hint there, which will take me on another blackboard, can I discuss question 7? Were you going to ask me about number 7? Yeah, I was. You were? Okay. Yeah, all right. We get the answer. Okay. So question 7 is about the accuracy. So here's the correct number. This is my e to the I omega t. That's the correct number that I should be multiplying by. And the actual number that I'm multiplying by is that one. Or in the forward Euler case, it's that one. And so I'm comparing the one-step accuracy. So let me compare one-step accuracy. Yeah, so this is the topic now of order of accuracy. This is the question 7. And it amounts to comparing the, so what is one delta t step in the continuous case? So how much does the eigenvector x, what does it get multiplied by if I take a delta t step in the differential equation? So this is the exact delta t step. What the finite difference won't get exactly right. Step delta t. The differential equation. Of course, I'm looking at ax equal lambda x. The differential equation multiplies x by what? What's the exact growth factor, you could say? If my equation is du dt equal au, that's the differential equation, And I'm supposing that I'm on an eigenvector x, so that the solution is e to the I omega t, or e to the I lambda x. Now, what happened over a delta t step? This is the answer, like running along for all time. All I'm asking you to do is, if the step is delta t, what's that number? I mean, that number is telling us how much it grew in that delta t step. And of course, it's e to the I omega delta t. That's the exact growth factor. That's g exact. In one time step, the eigenvector gets multiplied by that, because that's the amount of time that elapsed. And what's the approximate growth? The growth factor from trapezoidal is just what we wrote down here. 1 plus delta t, or lambda delta t. Yeah, maybe I'll stay with lambda rather than I omega. Just e to the lambda delta t. And this was 1 plus delta t over 2 lambda divided by 1 minus delta t over 2 lambda. So question 7 just says, compare that with that. If thinking of delta t as a small time step, if delta t is 0, then of course the e to the 0 is 1. If delta t is 0, I get 1 here. They're correct if delta t is 0. That's no big deal. How do I study, how do I understand what happens for small delta t? This is like comparing. I'm comparing this exponential for small delta t with this guy for small delta t. How do you make comparisons for small delta t? Well, that's what Taylor series is all about. Let's do the Taylor series. What's the series for the exponential? If delta t is small, I have e to some little number. Tell me, start me out on the exponential. 1, thanks. 1 plus, right, plus lambda delta t plus, this is the exponential series. There are only 2 series in this world that are worth knowing. Really, that's literally true. In calculus, you study all these infinite series. There are 2 that are important, that are worth remembering long after calculus, and e to the x, e to the whatever, is one of them. Okay, what's the next term? Over 2, lambda delta t squared over 2, and then there's a cube guy, and if you don't mind telling me, what's the denominator in that one? It's 3 factorial 6. Good, and onwards. Okay. So that's one of the series that everybody should know. Okay, how are we going to deal with this guy? How we want to expand that. So what's my goal? I want you to expand that in powers of lambda delta t and compare with this and see how where do they aren't going to be equal, right? At some point they're going to be different, but at least they should start out equal. So can you do this? So here's the heart of problem 7. What do I do? How do I expand this in powers of delta t? Do you mind if this is just a number, let me put it times 1 over it. So this is times 1 minus delta t over 2 lambda inverse, right? I just bring that up as a number. So it's this guy times 1 over this guy. What do I do? This is, here's the moment when, the math tools get used. And I'm well aware that, it's like years since you did calculus or series or whatever, and those tools get rusty. And the point is that they're really genuine tools that we can now use. So what do you think? What shall I, this is the sort of like problem one. This is the one coming from the denominator. This is 1 over 1 minus x, you should say. So I have a 1 over 1 minus x deal. And what's the series for that? I said there were 2 series worth remembering, and sure enough, the exponential was one of them, and now we're ready for the other one. What's the series for that guy? 1 plus x, good start, plus x squared, right. X squared plus x cubed, and so on. Real simple. It's all the same stuff with no factorials. Those are the 2 series to know. The exponential series and the geometric series. Right. That's the geometric series. Okay, so that's what I've got out of this stuff. Can I write it below? I have 1 plus delta t over 2 lambda. Let me just call that x for the moment. Delta t over 2 lambda is my x. 1 plus x, and this is 1 over 1 minus x, which you just told me is 1 minus plus x squared plus x cubed, and so on. And now I've got to do that multiplication. Okay, x is, remember, this is x. This is my x. I'm just save space. Can you multiply those guys? So that's 1 plus x times this lot of stuff here. What do I have all together? Well, the 1, what's the next term? 2 x's? Everybody spots the 2 x's there? And then the next term? You have to get these terms right, because we plan to compare with this guy and see how many we get. How many x squareds are in there? Is it 2? Looks like 2. 2x squareds and 2x cubes and so on. Yeah, that looks right. Okay. Now I'm ready. What am I ready for? I'm ready to say what x is. X is this delta t over 2 lambda. So what is it? What have I got here? 1. What is this guy now? 2 x's is delta t lambda. Is this good? Yes, right? We're pleased because the 2x is the 2 of these is delta t lambda, and that's what we wanted to match. Absolutely, delta t lambda or lambda delta t. Now let's keep going. By the way, if this first term hadn't matched, we would be extremely surprised, right? Because that first matching is only saying that my difference equation is like consistent. It's a reasonable creation out of the differential equation. And we knew that. The question is, how much further are we going to get? Euler will not get any further. With Euler, the next ones will fail. But I think with trapezoidal, the next ones are going to work. Does it work? You're like we're holding our breath, right? 2, now I'm going to put in x squared and see about this term. X is what? X is this guy, delta t over 2 lambda. Delta t lambda over 2 squared. And now you get the fun. Because you're going to compare this term with what? With this term. And are they the same? Yes, yes. So that's the way you see that you got the extra accuracy, which Euler did not give you. But so that's why the trapezoidal rule is a second order accurate method. Okay, you may say that I went overboard to say all that. You may say, I didn't ask that question. But it's the right question to ask about order of accuracy, and it's what problem 7 was intending to bring to maybe I called it H in problem 7 rather than X here. Well, oh gosh, I realize I still have I'm supposed to come back to this one, but some people might have other problems that they're interested in. Let me, because time is pushing along, and the solution to this one will post, let me at least offer the possibility to ask me about something completely not 6 or 7 here, but something entirely different, like what's the first question on the quiz or anything. And that, let me say, I'll hope to know by Tuesday. I love to teach, but making up exams is serious work. Anyway, let me move up, open a board and open to another question of any sort, any place, chapter 1, chapter 2, whatever. Is there anything? So I know that you're in the middle of this homework, so I can say a little more here about that number 6 if you want, but I wanted to allow, yeah.
Very quick question. You wrote that the exam includes up to, you got like triangle and A's going on there?
The A and the, from today's lecture, this was the incidence matrix.
Okay. Okay.
And this was the A transpose A that's probably still on the board somewhere. Yeah, yeah. So this is what, so this is the A, which you should take in and be able to create if I gave you the graph. And this is the A transpose A. So it's through today's lecture, right. Yeah. Next lecture I'll be talking about the A transpose by itself, which involves Kirchhoff's current law. It's beautiful, beautiful. A transpose W equals 0. But I think this part was straightforward enough to be able to add this to our list of problems which fit the framework. Yeah, yeah. So that's what that was about. That doesn't mean that this will be on, but it could be. Right. Okay. What else? You guys are patient to come on. Yeah. Thanks.
That geometric formula, the expansion. Is that
Yeah.
It's only valid when x is less than 1.
It's only valid when x is less than 1. Yeah, so that's now the math point, that this expansion for e to the x is valid all x's, because you're dividing by these bigger and bigger numbers. But this one is only valid up to x equal 1. At x equal 1, we're getting 1 plus 1 plus 1, and we're getting 1 over 1 minus 1, sort of infinity matches infinity. But then if x goes up to 2, yeah, what happens if x is 2? It's sort of not good, but you know, mathematics is never completely crazy, right? If x is 2, what does this say? What have I got on the left-hand side? Negative 1. And what have I got on the right-hand side? 1 plus 2 plus 4 plus 8. I should not allow this to be videotaped. But that's actually not so completely crazy. In some nutty way, you know, that could still make some sense. I won't. That certainly will not be on the. So you're right that x should be less than 1. And of course, it will be here because I'm looking at little delta t's. So my delta t, my x was this thing, and my delta t, the time step, was small. And somehow that tells me, actually, this is a good indication. It gives me the units, that stability and things going right will depend on lambda delta t. Will depend on lambda delta t. That's the key parameter there. That's like the dimensionless parameter or lambda delta t over 2 or whatever. But lambda delta t is the key, and highly important key. It tells us that as lambda gets bigger, as the matrix has bigger eigenvalues, delta t has got to get smaller. And I mentioned stiff equations. Stiff equations are equations where the eigenvalues lambda are out of scale. You know, you might have 2 eigenvalues, one of size 1 and the other of size 10 to the 4th, because you've got 2 physical processes going on at the same time. And those equations are tough because that 10 to the fourth guy is forcing your delta t to be really small. Whereas the action the true, real solution might be controlled by the lambda equal 1 guy. So to follow this slow evolution, you're having to take very small steps because on top of that slow evolution with the lambda equal 1, there's some very fast evolution, maybe with lambda equal minus 10,000. Yeah, so that, there's a lot happens here. And you have to think, okay, is there some way around that box? And because forward Euler would not get you through. Yeah. Okay, thanks for that question. You got another one. Okay.
Yes. So then if you weren't using small enough time steps, it wouldn't even be second order accurate?
If you weren't using small enough time steps. Okay. For trapezoidal, let's say?
I mean, that expansion wouldn't hold if you were using a lambda.
Well, the expansion is really intended for small delta t. Yeah, it's not intended. I'm not, you see, I never added up the whole series. I just compared a couple of terms to see how am I doing. And I got the extra term to match from trapezoidal that I didn't get from Euler. Yeah, so what's to say? If you took delta t too big, what would happen in the trapezoidal method? Well, you would stay on the circle because the absolute value of this thing is truly 1, even if lambda is enormous and delta t is way too big. We still had complex conjugates, and their ratio was 1. So we would not leave the circle, at least in perfect arithmetic, as everybody says. You know, if we didn't make any round-off error, we would not leave the circle. But boy, would we skip all over the place on that circle. So if we took delta t too big, we would be completely inaccurate. We wouldn't be unstable for trapezoidal because it would stay on the circle, but it would be the phase would be completely wrong. Yeah, yeah. So it'd be a complex number of absolute value 1, but it would not be close to the exact growth factor. Yeah. Well, so many things to say. You know, I realize that the course moves along pretty quickly, but this topic of numerical methods for differential equations, that's a core part of 18086. So I'm like anticipating here in just a couple of days. What really takes longer is the stability and the accuracy and the best choices for time-dependent problems. Yeah, yeah. Okay, always good questions. Anything else just on your mind of any sort? Yes, thanks.
On the textbook, page 114.
114?
Yeah, there's a figure 2.7.
Okay. 114, figure 2.7. Oh, yes, okay. Oh, yeah.
I'm curious about how this shape is done.
So let's see, so that has a bunch of figures. So that, in order to say for everybody who's not looking at the book, those figures are about the problem we've discussed here, or the model problem, where we're on a circle. So do I have space to draw a circle? Well, let me just make space here. Okay. So page 114 has that model problem that we've drawn before. There's the exact solution. It's the phase plane. There's u and there's u prime. And the u was cos t. So the u prime was minus sine t, and we travel around the circle on the exact solution. Energy constant. U squared stays 1. U squared plus u prime squared stay 1. Now, which figure was it you wanted me to look at? So,
Could you explain the meaning?
of any of them?
Yeah.
Okay, that's fine. Let's see. Is trapezoidal on that one? Yeah, trapezoidal was the first one. Okay, so figure 2.6 shows the trapezoidal method moving around the circle. So what happens? Yeah, thanks. That's a very suitable question. Okay. And I took, in that figure, I took how long does it take for the exact solution to get exactly back where it started? At t equal what do I come back? 2 pi. T equal to 2 pi, I'm right back where I was, right? Cosine has period 2 pi. Okay. Now, suppose I take suppose a single step of size 2 pi would be really ridiculous, right? I mean, delta t, I want to now delta t. So let me take, in that figure, I took delta t to be 2 pi divided by 32. So I'm taking delta t to be the 2 pi that would bring me all the way around, but I'm dividing by 32. So what does that mean? What does the exact solution do at those steps, 32 steps? It goes on the circle, 32 equal steps, 360, or 2 pi divided by 32 radians every time, comes back exactly there, the exact solution, and right where I started. So it's like following a planet. Now I do it by finite differences. And so now I'm going to follow the trapezoidal rule, just what we've been talking about, with that time step and with the equation. Everybody remembers the equation was u prime equals, do you remember what the matrix was in that equation? Oh, this is the derivative of it, and this is u prime. Sorry to squeeze this in, but u prime is u prime. U double prime is minus u. Now we know why that matrix was good, right? Why is that? That's my matrix A. Why is it good? Because it's exactly, it fits. A transpose is minus A. It's anti-symmetric. Keeps me right on the circle. Okay, now trapezoidal method keeps me right on the circle, 32 steps. And so the picture just shows where it goes after 32 steps. And 32, 32, does it come back there? Well, not exactly, right? We don't expect the finite difference solution to be exactly in sync with the cosine t, the real one. But it's really close. I think in that figure, your eye can see that that's sort of a double point there at 2 pi. I put a little arrow indicating small phase error. It misses by a little bit, right? It misses by a little bit. And actually, roughly, what does it miss by? This was the point of the order of accuracy stuff. Roughly what size is that little error? That's what we did over here. The term that we got wrong was a delta t cubed at each step. Can I just tell you the answer? The error here is of size delta t squared. Because over here we matched those series and we found the error was delta t cubed. That's in a single step. But now we've got like 1 over delta t steps. You see what I'm saying? That if the error was delta t cubed per step, and I have 1 over delta t steps to get somewhere, or 2 pi over delta t or whatever, then that gives me delta t squared. So that little error there is my error of size delta t squared. And that squared tells me I've got a good method, at least decent, second order accurate. And the trapezoidal rule is sort of the natural one. Well, okay, so that's a full hour mostly devoted to 2 or 3 things. Actually, the eigenvectors came into it, and the energy conservation came into it, the stability matching series came into it, and the picture. Okay, so I'll see you Friday for more about these guys. And then Monday evening, please ask me everything you want to on Monday evening. Okay. Thank you.